So thank you for inviting me. It's a beautiful day. I was in Potsdam last time when VLDB was in Berlin in 2003, I think. And we only came to the palace, Sanssouci, and we got in. I didn't see all this, the lakes and the beauty that you have. So thank you for inviting me. So as I agreed with Felix, this is more of a tutorial talk than about my research. My research is in cloud computing at the moment and privacy issues and various things related to managing large-scale data. But recently we've been very interested in blockchain, and I've been working with my colleague Divi Agrawal and then three of our students, Mohammed Amiri, Sujaya, Maya, and Victor Zakhari, on a tutorial that we gave last VLDB in Rio, and we are going to give a variation on it in Sigmod in Amsterdam. So I thought I'll give you, it's a 3-hour tutorial. So what I'm going to try and give you is a sense of some of the interesting challenges that arise in this context. And I have to say that from a technical point of view, what drives me is not the cryptocurrency, so don't ask me about money issues. I really don't know, and I don't do the stock market at all. I'm interested in blockchains as an artifact or something that brings in 3 important components of computer science, 2 of them with which I like to work in, which is databases, distributed systems, and the third one is cryptography and security. So I'm going to be talking about some of the challenges and how the decisions to build blockchain were made and try and relate them whenever I can to database issues and or distributed systems issues. Of course, I'll need the cryptography since it's kind of underlying a lot of the stuff, so I'll present it. This is not my particular expertise, but I've been collaborating with people trying to understand more about those things. So just to lay the groundwork, there is a lot of hype about blockchain. This is from Newsweek. They had it on the front page. It's a block party. Everybody thinks it's going to solve everybody's problems. It's like the hype that we have that computer science goes through every now and then. There was a New York Times opinion ed that said it's time for online voting, and if you read the details, what does it say? The solution to online voting is to use blockchain. So blockchain is going to solve all our problems. I don't show you here actually the article itself, but it's very interesting reading the article on this voting issue because it uses a lot of terms that I would have assumed you have to be a specialist to appreciate. Like they talk about concurrency, they talk about replication. This is a political opinion page. They talk about provenance, persistence, double spending, terms that they are expecting now that the layman will actually appreciate these things and relate to it. So this is just a part of this. I'll come back to this issue later on, depending on the time. But let me start with basically the origins of blockchain. And the origins come from Bitcoin and support for cryptocurrencies. So traditionally, we have transacted our transactions, our money transactions through banks. And banks are these very big established entities. You have a bank in a city and you can recognize it. It exudes trust. We trust these banks. These are institutions that have been around typically, and we trust them. So I put my money in the bank, Felix puts his money in the bank, and if ever we want to transact with each other, typically we would write a check to each other, and then each of us gives our check, or he gives his check to his bank, and then the bank talk to each other. Maybe they will pass money, more likely they will not pass money, they will just keep track of how much they order and what is happening. And I trust that this all has happened. So interactions occur through these trusted entities. Traditional banks have a lot of things that we are familiar with. For example, this example of a check. What we do is we do transactions with each other, and we write checks, and at the bottom right, I will sign my name. When Felix gives me some money, I sign my name. Now that signature uniquely identifies me. It's an identification of me, and if you go to banks, traditionally, they will actually look at the signature, and they should have your signature and verify that this is your bank, this is really your signature. So a signature becomes my identity. If you have my signature, nobody can forge it, and it is an identity. So this is one aspect. Another aspect is the bank keeps track of all that has been happening in this bank. So all transactions, all identification of anything that is happening, and it's typically stored in an append-only structure. If you've studied databases, we do this all the time. And it's basically a long ledger that is efficient, and you add information to it, everything that is happening. You can retrace the whole history of things based on this ledger. Finally, and most important, you have transactions where people take money from one identity to another, from one entity to another. Banks, and actually a lot of the database transaction management technology that was developed early on by Jim Gray and others, was to basically guarantee that these transactions are executed correctly, atomically, in an ACID manner. So we have concurrency control protocols that serialize transactions, make sure that if I'm giving 2 checks, I don't overspend my money. There's always, if my balance is a certain amount, the transaction management is going to abort one if something is going to go wrong. Lots of these things. Typically, we have the log is persistent, and how does traditional systems ensure persistence? Using a disk. So that's why we have all these significant recovery protocols. The disk is immutable. We trust the bank. We trust the employees in the bank that it's going to be tamper-free. There are all these very nice properties. Now, I want to put this as background for what I'm going to be talking about later, or very shortly. So basically, banks are reliable, trustworthy, and fault-tolerant. We just come Bitcoin, and according to Nakamoto, this fictitious kind of personality, mythical, is that we want to get rid of these trusted banks, and we want to replace it with this network of peer-to-peers who are going to collectively replace this trust and will collectively give trust and be able to transact things. So it's a peer-to-peer system. And let us look at a very high level at what they did, what they proposed to do with the few things that I talked about in terms of the checks, the transactions that take place. So the first thing is identity. Identity is very important. What happens in Bitcoin and blockchain is you use a public and private key signature system. They are mainly used for identification, not for security. So it's just a little bit different from the standard approach. I'll go more into details, but they have a ledger, and that is the blockchain. It's a linked list, literally. And then we have transactions. Basically, you have transactions that are happening between individuals. I take my money, I give it to somebody else. We need mechanisms that ensure serializability, and they will develop techniques called mining or proof of work in the context of Bitcoin in particular. There's also going to be the blockchain, and the blockchain is going to be persistent. Rather than having persistence on a disk, what we're going to do is we're going to have multiple copies of it, lots of copies, actually copies with everybody, if everybody wants it. So persistence comes in a different way. Also, you are going to have tamper freedom and immutability, and they are going to use hash pointers to ensure that. Let me talk about some of these concepts in a little bit more detail. So the public key, basically, you can generate, given a key size, I can generate, this is cryptographic techniques to generate a private key and a public key, or a secret key and a public key. So you have two of them, and the public key is my identity. So once you know my public key, you know how to talk to me. If you want to refer to me, you can use my public key. I can generate multiple public keys. That's okay, but if ever you want to do anything with me, you refer to me by my public key. The secret key is my signature. I can use it, and the public key can be used to verify that this was actually my signature. So the secret key is private, the public key is public, and if you have a message, you can encrypt it using the secret key, and you generate a message, an encrypted message, which can be decrypted using the public key. That would have been the traditional approach. If you have a document, you can sign it, and once you've signed it, it generates a signature that is associated with this document. Unlike in the check example of the human signature, where my signature is the same whether I'm signing this check today or tomorrow's check or the letter I give to Felix. In this case, the signature is associated with the document. They are one entity with each other, so the signature is actually tied to the particular document immediately. Once I have signed something, I can publicize it, and anybody can use the public key to verify that this is really my signature for this document, and you get either it's valid or invalid. So this is the way public keys and private keys interact with each other. And I want to emphasize, mainly we are thinking about using them, or my emphasis will be for identification rather than privacy issues. So Bitcoin is going to be a chain of coins that are going to be going around between individuals in the system. So a coin owner can sign it and say, give it to Alice, given Alice's public key. So using Alice's public key, we identify that the money is going to Alice, and using my private key, I'm going to sign it. So everybody who sees it can verify that I took this money and gave it to Alice. So if we have a Bitcoin like this, and there is I wrote that I'm giving it to So Alice has this Bitcoin. She's going to say, I want to give it using the public key of Bob to Bob. So that's the identification. She's going to sign it and then wrap it up together and send it out. Now we have a new entity, and it has Bob and the signature, and anybody can use Alice's public key to verify that really Alice gave the money to Bob. Yeah, so it's the same story. Now Bob has the money and has a signature that says that it belongs to him. He can take it and give it to Carol. So he can wrap it up, give it to Diana in this case. So he had money that was given from Alice to Bob. Now he's going to say, I want to give it to Diana. I'm going to sign it using Bob's secret signature and sends it out to the universe. Okay? So you can keep on doing this. So given a coin, you have a chain of commands that show you where it was being transferred and who got it from whom and its entire history. Actually, its provenance is recorded in that history. So in general, I can take a signature, Alice can give it to Bob, Bob can then take it and give it to Diana, and so on. There are lots of interesting questions we can ask. One of them is, how do I combine these two signatures like this together? So I've signed it. I don't want to have ever expanding documents. So I want to come and find them. How do I guarantee that if Bob has a coin, he doesn't double spend it, give it to Alice and give it to Bob? You want to be careful about these things. So there are lots of questions that have been around in the cryptocurrency world, and what's interesting is how they dealt with it in this context. So let me talk about the first problem first, which is the combination function, which is going to be used a lot, and that's hashing, something that all of you probably know about. Basically, hashing is used often to take an input that is variable length and to make sure that I can put it in a fixed length output in a way that it's probabilistically uniquely identifies the input. So no two different inputs can map to the same thing. So signatures and public keys are combined using hashing, and taking any length, we want it to be put in a fixed output size. And typically, they use SHA-256, which is a well-known function that maps things to 256 bits. It's efficiently computable. It's very easy to compute, relatively easy, and it has certain good properties. It's collision-free, meaning that two different values with very low probability are going to map to the same item. So so if you have it to the same output, they're going to be different. And there's hiding, which means that given that I have h of x, which is infeasible, it's a one-way function. So given the output, it's very hard for me to figure out the input. If I give you the output, it's very hard for you to figure out the input. As a result, it has this nice property, which is puzzle-friendly, which has been used before, but here they're going to use it extensively, which is the fact that I can give you a puzzle. I can tell you, given a certain string, a certain ID, can you find something to attach to it, to concatenate with it, so that when you hash it, it gives me a particular value that is in a certain domain? Figuring this out, given the one-way function that it cannot go from the output to the input, it's very hard to figure this out. So it takes a lot of effort. Actually, the only way to do it is to exhaustively span the whole space and try different approximations, try different attempts, and eventually one of them will succeed. But if the problem is hard, it's going to take a long time. So all these are properties of the hash function. They are used in different parts in Bitcoin or in the blockchain that we are describing in different ways. So Bitcoin uses SHA-256. So given the money with the signature from Alice to Bob, and given that you want to send it to Diana now, what we're going to do is we're going to SHA-256 it, and we get a unique string, unique probabilistically, because obviously the domain of the input was much bigger than the domain of the output, but the hash functions are designed in a way to guarantee this. So for example, if I have SHA-256 of ABC, all of them lowercase, I get this string of hex. If I change one letter from the lowercase to uppercase C, you get a very different output. So knowing one output doesn't help you figure out another input at all. They are so different. It's so hard. So it's just very difficult to do. So now we have addressed the combination problem. We're going to use the hash function. What about double spending? Let me talk about double spending. So if you have real money, if I took €5 and gave it to Felix, I cannot take the same €5 and give it to Alice, because he already has my money. But if I have a string of bits, I could theoretically give it to Felix and give it to Alice and get away with it. So now this is the problem of double spending, is that this ability to regenerate things. In traditional database systems, we deal with this using concurrency control. We have guarantees that there are certain properties, invariants that the database satisfies. There's no account that goes below 0, and if a transaction goes below 0, we're going to check it and are not going to allow it to execute. So there are techniques that have been developed. The question is, how can this be done in the context that we are talking about? So we have some money that was given from Alice to Bob, and what Bob can do is make two different versions of it and give one of them to Diana. The public key of Diana is up there, and give it to Marty here. And now he can sign it, it would be verified using his public key, and now he can get a car from Diana and a ring from Marty and get away with this. So how do we avoid this problem? How does blockchain avoid this problem? So there are possible solutions. For example, we could do a centralized approach where before Bob sends the money to anybody, they have to go through the entity. This is what we do when we give it to the bank. I give to the bank, and then I say, send it to Marty and send it to Diana. So we could have a trusted third entity that could solve the problem. And it would say there is an issue. I cannot spend both $30 and $20 from the bank account. This is the traditional solution. We want to avoid this. We don't want to have these trusted third entities. We want to replace this with the Bitcoin solution, which is the blockchain solution, which is a decentralized solution. I do not want to have banks or third-party entities that are trusted. We just have the community that is going to collectively give the trust. So it's going to be a network of nodes, and everybody in the system has a ledger, has a history of what has been happening in this system. What is the history and the provenance of the different currencies and transactions that have been executing. So nodes will agree on the transaction order and serialize transactions on every coin to prevent double spending. So this is an old problem that has been studied a lot in distributed systems, which is the finite state machine replication approach. You have something that you want to make sure is reliable, whether it's a process or even updating a file. I make multiple copies of the file, and if I execute the same operations on the different copies, they are both going to reach the same state. So if I have a log of all the operations and they are all ordered in the same way, the final state of all the replicas is going to be identical. So that's been a problem that has been around. Let us see how this is being approached in the blockchain approach. So the ledger is a blockchain, and instead of having one transaction at a time like I was describing, we're going to have a block. And each block is going to have a collection of transactions, a set of transactions. The blocks are going to be chained with each other using pointers. So you'll have a pointer from one block to the previous block, instead of having just a sequential log. So it looks something like this. I'll have a block with n transactions, and then I have another block with n transactions, and then a third block, and so on. We'll have a linked list, literally, of blocks. And the question is, what are these pointers like, and how to add to the head of a linked list? This is the age-old problem of linked lists. So where is this ledger going to be stored? It's going to be stored everywhere in the network. Every process that wants to have a copy can have a copy. So you can have a copy wherever you want. How are we going to ensure that nobody can change some entries here and Alice might take some money and make it go to her instead of going to Bob, for example? So what's going to be used is a sequence of hash pointers. Instead of having simple pointers to the previous block, each block is going to have two different things. It's going to have a pointer and a hash of the previous block, using SHA-256 again. Since it's very hard to reverse the output to the input of a hash function, if anybody tampers with any of the blocks, the entries in the block, it's going to be detected. So if I have this block, on the second block, I'm going to change these two to two other transactions, then this hash is not going to hash to the right amount, and hence everybody will identify that there is tampering that has happened with this transaction. So hashing is what's going to be used to detect inconsistencies, and this can propagate throughout the chain if you want. So it makes it hard. Now we come to the interesting part. We have all these individuals who are part of the blockchain, who have copies of the linked list of the blockchain, and we want to make progress. We want to add a block to this linked list, to this blockchain. So the ledger is everywhere. To make progress, the network, somebody's going to collect a bunch of transactions and is going to try and put it at the head of the queue. The blocks in blockchain, in Bitcoin's implementation of blockchain are fixed size. They are all 1 megabyte, so they are all fixed. And every node that is going to add a block to the head of the queue needs to do two things. It needs to make sure that all the transactions in the block are validated against each other. So we are doing the concurrency control work. We are making sure that there is no conflicts, there's no double spending, nothing that is happening within any given block, as well as the previous blocks. So you look at the history and you make sure that for every coin, its lineage that is coming from the very beginning is consistent, and that what this new block is doing doesn't violate that. So here is where the validation of the blockchain is happening, of the concurrency and the double spending is happening. The problem is that I could be trying to add a block and you could be trying to add a block. How do we make sure that we don't have this situation? This is the problem of having consensus among a set of processes that are in a distributed system. So we have a distributed system, we have different entities, and each of them is trying to add a block to a linked list. So we have a consensus problem. This is a problem that has been studied a long time ago, for a long time. In particular, it was made famous by Leslie Lamport. There are two kinds of solutions for this. There's a lot of literature for synchronous systems and for asynchronous systems. In blockchain, we are going for an asynchronous approach. So those are the protocols that are of interest. And the typical problem is formulated as you want agreement, that all the correct processes agree on the same thing, whether to add or not to add a particular block, and a validity, which is a progress type of condition, which is that if the person who wants to add something is correct, doesn't fail, then all the correct processes agree on its value. They all do what it really wants to do. This problem has been studied in two different contexts: crash failures, and the most famous at the moment in an asynchronous system is Paxos, which is used by Google, for example, in its Chubby component for Bigtable, in Spanner, which has been used. Its variations of it are in Amazon's, etc. I mean, there are various implementations or variations on Paxos that have been used. They all assume that if a machine fails, it just crashes. So you lose everything that's in it, but that's it. So replication can save you in this context. The more complicated environment is where we have what's called Byzantine failures or malicious, where sites may lie about what they want to do. So I give $5 to Felix and I give $5 to Alice at the same time. So I could have this issue. The most significant protocol in this realm is what's often called practical Byzantine fault tolerance, or Byzantine fault tolerance, and that was due to Castro and Liskov. Paxos is due to Lamport. And both of these protocols have been around since the end of the 90s, so from the last century. Both of them have an interesting story in the sense that they were proposed and it took a while actually for people to use them. It took for Paxos to be actually appreciated. It didn't happen till Google started using it, and in 2005, 2004. There are some important impossibility results I should tell you, which is that in an asynchronous system, we have a very fundamental result, that's Fisher-Lynch-Patterson result, which tells us that I cannot guarantee termination. So you can guarantee safety. We will not do anything bad. We won't do contradictory things. Not one will pick one and another one will pick 0. But guaranteeing liveness or termination is not guaranteed. However, most of the time it works. So that's why in practical systems like Paxos, they actually use it. Yeah. In synchronous systems, there are lots of other solutions, but basically you have a third type of failure that you cannot tolerate. So in a synchronous system, you can at most have a third malicious failures to be able to make any progress. And it's interesting that even in the asynchronous malicious case, the assumption is that at most a third of the processes are faulty. You cannot have more, at most a third. So let's go back to our problem. So this was like a slide summarizing a course in distributed systems. So now we have the same problem. We have a bunch of processes that are trying to agree on something, which is to insert something at the head of a queue, at the head of a linked list. So can we use Paxos? So ideally, somebody like this would get this node, this extra new block, and try to add it to the blockchain and tell everybody, I won, I am the leader, I got consensus, I am going to broadcast this value to everybody. So let's look. Paxos has some problems from this point of view. The most fundamental problem, in my opinion, is that it assumes that we know the number of processes in the system. For Paxos to work, for all of these consensus protocols to work, you need to have a notion of majority. You need to be elected as a leader. You need to make a value fault tolerant by replicating it on a majority of sites. Once I say majority, you must ask me, what is your n, so that I can divide it in 2 and add 1. In blockchain, we do not know n. We do not know who the participants are. And hence, the traditional Paxos approach will not work. The traditional consensus protocols in general will not work. But this divides the world of blockchain into two kinds. There are, which is the emphasis of my discussion today, permissionless systems, where basically we don't know who's around. And those, they cannot use consensus protocols. However, there are blockchain proposals for environments where the number of entities that are dealing with the issue are known. So for banks that are trying to transact with each other, they could use a blockchain to give us the benefits of persistence, lineage, etc. So for the permissioned environments, you could use blockchain. And depending on your failure model, you're going to maybe use Paxos or not. If you only assume that the entities you are transacting with can crash, can fail, then you could use Paxos. The problem in a blockchain setting, in a Bitcoin, is nobody trusts each other. From the very beginning, I was telling you, we don't trust each other. We need these signatures, we need identities. So even in permission systems, you often have environments where the different entities do not trust each other. So the natural question is to say, well, can I use PBFT, the malicious version of consensus? And the answer is yes, and this is what, for permissioned systems, where the number of entities are known, people have proposed, and there are various proposals that use Byzantine fault tolerance to achieve consensus and hence solve the problem. But in a permissionless environment like Bitcoin, where we don't know the number of entities, even though PBFT tolerates malicious behavior, it's not going to be helpful because it assumes we know the number of sites in the system. Is this clear? So this connection between the two different approaches and why the classical approaches have a fundamental problem. We really need to rethink how to do consensus in this new model. And what Bitcoin does is the proposal that is in the Nakamoto consensus protocol, which is basically this idea of mining. So basically, instead of trying to use communication, which is typical of consensus protocols, to get agreement on I am the leader. If I can get 51% of your votes, then I know now nobody else can get 51% of the votes. And hence, I can dictate what I want to be at the head of the blockchain. If I don't know how many people are here, what they are proposing is, let's have a hard race. Let's say it's a marathon. If we all run in this marathon, it's very unlikely that two of us would reach the end at the same time. And so we are going to use this approach. We're just going to have a race, a hard problem, a puzzle for everybody to try and solve. And we know it takes a long time, about 10 minutes actually, to solve. And so it's unlikely that 2 or 3 of us will reach the end at the same moment, will solve this hard puzzle at the same time, and hence whoever solves it is going to be declared the winner of the consensus without any communication. It's completely local. So this is what's called mining, is you give them a hard problem. I'm going to discuss some details about the hard problem, but basically give them a hard problem. Everybody knows this hard problem. Everybody can work on it. Once I've solved it, it's very easy for everybody to verify that I solved it also. So if I won the race, everybody sees me, it's clear. So how is a block created? There is somebody, a miner, but a miner could be anybody. So anybody can be a miner, anybody can be creating transactions, at least in the idealistic setting. In the real world, things have evolved in a different way. So there is a blockchain, this miner has a blockchain, and there are all these clients, Alice, Bob, Marty, Carol, sending transactions to each other. They're going to, each time one of them has a transaction transferring some amount of money from some person to another, what they do is they send it out to everybody who's interested, every possible miner. So they send it out. So he gets it, and you and everybody else, and they put it in their block. They are creating this block. They keep on getting transactions and putting it to the block. While they are putting it in the block, they are verifying the validity, that they are not conflicting with other transactions in the same block or with transactions that are preferred. So it's giving us the whole history of it. Now he has a block, this miner. If he succeeds in adding the block to the blockchain, he gets a reward for the effort that he's going to do, if he succeeds. If he wins the race, he's going to get a reward. And this is how money is created in Bitcoin. Every time you mine a new block, you can create money and give it to yourself. And given that you will have proved that you won the race, this money will be really yours. So this is how money starts getting generated. So it's added to the blockchain. So here is what abstractly the details of this blockchain are. I'm not going to go through all the details, but obviously there are the transactions, all of them that I got, as well as the reward, and then a header. The header has several important components. There are some version numbers. There's the previous block hash, which I referred to before, which tells us that it's not tampered. It has a Merkle tree of all the transactions that are in the blockchain. So there's a summary. You can think of the Merkle tree as a summary of all the transactions that are in this blockchain. So instead of having all of these entities here, n transactions plus 1, I'm going to summarize them. It's a tree that hashes eventually so that you have a fixed size hash that represents the content of all these transactions. We have a timestamp, and critically, we have this thing in red, which is called the nonce. The nonce is the solution of the puzzle that I'm trying to solve. So what a miner does is he takes the contents of the header, SHA-256 it, and tries to find the nonce that is going to make it have a certain characteristic. And the certain characteristic is that it is less than a certain difficulty. And I'm going to explain a little bit more about these. But this is the context in which things are happening. So let's talk first a little bit about the reward, since there are some interesting details here. The reward is self-signed. It's the way of generating coins. The value is halved every 4 years. So every 4 years, the money the reward lessens. So eventually, there's going to be no reward. And a miner gets money basically now more from getting reward for every transaction that he mines, he gets some money, some cutoff on it. Now it is 12.5 bitcoins per block. And this is the incentive for us to work, as well as the deduction on each transaction. What about the SHA-256? So the difficulty is dynamic, is a dynamically adjusted difficulty, so that it takes about the same amount of time for as the system evolves. So even as the hardware evolves, the difficulty adapts to it, so that the time it takes to do the mining is approximately the same amount of time, which is 10 minutes. So what is the difficulty? We know that the output of SHA-256 is 256 bits. What you're going to specify is that the difficulty is the number of initial bits that I want to be 0. So I want all of these to be 0. So that's the difficulty. So I'm going to SHA-256 the header and look at the output. When I look at the output, I see, are the first D components bits 0 or not? If they are not, I have to try again. And since this is a one-way function, it's a very difficult thing, and I have to keep on trying. So, for example, here is a fairly realistic example of a header. And what we would like is to get 18 zeros at the very beginning. For example, this would be an outcome that would be good. Now, if you SHA-256 using all of this information and the nonce you start with the green 0, you're going to get this output, which has no zeros at the beginning. So, sorry, this is not good. Try again. You tried with, now we are going to try it with 1. You didn't get any zeros. Sorry, try again. You try it with 2. You got 7 zeros, not enough zeros. Try again. You keep on trying. And since this is an exponential space, it is a lot of work. And that is why mining is a lot of work. Eventually, you're going to get something. You get a string like this. This is all in hex. And you'll find 18 zeros, and you declare it, I'm a winner. Okay? So this is the mining problem. You can give it to 101 computer science, and you can write a mining piece of code. It's not deep. But it is a lot of work. It's a lot of computational power. And this is how computational power was used to solve the problem that we have instead of using communication, which was the traditional approach. Because we don't want to communicate with anybody. I want to do the work by myself, and if I succeed, I'm going... And anybody can verify it, because all you have to do is to take the nonce, SHA-256 it, and it's out. It's a one-way function. You know, it's like when you have multiplying two numbers is easy, factorizing is very hard. It's kind of a similar idea. So finding the nonce results in a problem. The solution is a set, and it's easy to verify if you have an answer, and cannot be pre-computed, cannot be stolen, nobody can benefit from it, and it's really hard. The problem is, so it's very unlikely that two of us solve it at the same time, but it is still possible. Yeah? So we've made it hard, but this is not consensus. This is not Byzantine agreement protocol that is guaranteed. If I get a winner, it's because I got a majority. or 2/3 or whatever the protocol is, and I know that nobody else is going to be a consensus. We've proven this. All of these are proven protocols, so we know that this is correct. Here, it's probabilistic, so it is still possible. So how is this going to be solved? You broadcast it, and we want to make sure that you don't have double spending. We don't want to have two different coins, two different branches. So I don't want one miner, green miner, to be there and a red miner to be here, because they just continue. Then you have a forking of the system. And you could have lots of problems. You could have double spending. You could have, it's not a linked list. What Bitcoin does is it takes a very simplistic solution, is to say that miners always try to follow the longest chain. So if you see two chains and the system is equally divided, most of us, half of us are working on the red, half of us are working on the green, probabilistically. Eventually, one of the chains is going to get longer. And then you broadcast it. Now everybody sees it, and any future miner is going to put their bets on the longest chain. And that's how they solve the double spending problem. So it is pushing it. So actually, you do not know that your transaction is really committed in a database sense, because if the green chain now is the winner, we are going to, all these transactions that were in the red block are going to be thrown away. So you issued a transaction, you broadcast it, it actually made it into the blockchain, but if another thread or another link or another fork made it better, it's going to be the winner and you are going to lose. So that transaction will be aborted. Hence, in blockchain in general, you do not know that your transaction is committed, again, it's probabilistic, until it's at least 6 deep. If each block is taking about 10 minutes to mine, then we are talking about an hour. You see what is happening. We are putting all these, or they are putting all these mechanisms that are really strangling, making the system slow, which is one of the main criticisms against blockchain. So, but this is what the paper proves, and I'm not going to argue it with you now, is that if a majority of people, 51% of the individuals in the system are not malicious, are not bad, then progress is going to happen. But if you have a majority that is bad, they could do the splitting, they could do the forking, they could do double spending. And there is an argument in the paper. It's at best an argument. So you could double spend if you have more than 51% of the miners, because I could do this, and then I do a transaction, and then I get some other transaction to be another block to get onto it. So the money is actually spent. Alice gave the car in return for some money, and then the malicious people go down below and start a longer chain on the other end. So that's the type of attack that can happen. So what we have is we have high latency, high transaction latency. It takes a long time to know that I have actually finished, that my transaction is committed. Consistency is probabilistic. Very low transaction rate. The throughput is very low. If you think about it, if you do the calculations, it's about 7 transactions per second. This does not work in the context of large-scale financial institutions. We talk about millions of transactions per second. This is what our current databases do. This is not what's happening here. A new block is added every 10 minutes. So this is a snapshot of the state of blockchain with all what's happening. what is the question is, what are people doing now? Now, there are lots of different issues that can be addressed. A big concern is the issue of throughput here. You could increase the block size. You could reduce the 10 minutes. But both of these will either favor the big miners, because if you have bigger blocks, you have to have more resources, etc. Or if you reduce the 10 minutes, the difficulty, then you'll have more forks in the system, because there's more likely that people will achieve this. So what has been happening is that in the permissionless world, there's been a lot of work on trying to incorporate Byzantine fault-tolerant consensus protocols into the blockchain. How do we do this? We have an open system. So, for example, there's a recent proposal by Silvio Micali, who's a Turing Award winner. It's called Algorand. Algorand, what they do is they elect a committee of individuals that are going to do consensus among them. But the protocol has to be also resilient to changes. So unlike traditional protocols, Byzantine fault-tolerant protocols, where you go through multiple rounds of communication and the individuals are known and they are fixed, the same set. Here, every round could have a different set of individuals. So there are very interesting, innovative ideas that are coming out in that respect. It's not only throughput and latency. There is the issue of the amount of energy that is being consumed by all these different mining protocols. Basically, you are consuming so much energy. People say it's as much as what Iceland uses in 1 year is being used in a Bitcoin to run blockchain of Bitcoin. So that's not responsible of us, I think, as computer scientists. Until 10 years ago, before the cloud and before blockchain, we were like the clean energy people. Now we are proposing solutions to important problems, maybe not so important, but at least to valid problems, but our solutions are hitting the limit of what we are able to do. And I think we have a burden as individuals, as computer science professionals, to address these issues. Can we do it using communication? I do not know, I'm not sure. But are there other techniques? And that is what is being proposed by various people. There are other types of problems that have more of a database flavor. For example, swapping coins across different blockchains. There's one blockchain which has Bitcoin and another blockchain that has Ethereum. And I have Ethereum and Felix has Bitcoins. We want to exchange 5 for 10, for example. We've agreed on some value. How do I guarantee that both of us who don't trust each other are going to be able to put the money in the blockchain and do the transfer in an atomic manner? So Maurice Hurley has been proposing solutions for this. There were solutions that were proposed in blockchain. I am working on this problem too. I think there are issues regarding atomicity and failure in this context. So I find the proposal of and then there is the permissioned world of blockchain. And there is, I think, a lot more leeway. And I think most of the hype is assuming a permissioned world, where the number of individuals is known and is typically small, but they don't trust each other. If there are transactions between banks and Visa and credit cards, they do not trust each other. They need the log, they need the properties of Bitcoin for that. I think there is a lot more potential, and there's a lot of work that has been going on. I am still searching for a non-cryptocurrency problem that really needs a permissioned blockchain. But intellectually, academically, I think it is an interesting problem. It's posing some challenges to us that we didn't think about before. I think I'll stop here.